Right, and this is close to the end of this week's journey in the discrete part of our courses. I shall add some remarks on what we call Markov chains. So this will be a discrete version of Markov chains. So the idea is that you have some configuration vectors, which will be again, say xn. This way will be x0n, x1n up to xkn, and this will be the probabilities of some system to be in one of the k possible states, right? So imagine, say, people watching the TV channel. So one of the states is no watching at all, and the others will be just the 48 channels on your TV. And that's the probability that you are watching one of them. And then you have this iterative model. So the xn plus 1 will be some linear matrix or some linear map value. So a matrix T times xn. And of course here the sum of xi is always 1, right? From I goes from 1 to k, because it's a so-called probability vector. So if we consider the situation that we have covered all the states, so simply adding none of the previous ones as a part of that, then we achieve that. So the probability will be 1. So each of the xi's is between 0 and 1, and the sum of all of those is 1. So that's a probability vector, right? Probability vector. And now we want to see that the probability vectors will be mapped to probability vectors again. So what is the requirement on T? So T will be a stochastic matrix, as we call them, and it will mean that the Tij are between 0 and 1, so all the elements, and the sum of the columns, so sum I goes from 1 to k of Tij is always 1, right? So that's the condition, that every probability vector is mapped to a probability vector again. So that's very easy. So we have got the notion of probability vectors and stochastic matrices. And now, if the transition matrix T would be not only stochastic but also primitive, so some power will be 1, will be only positive in all elements, then we can use the results from the previous video, and that will be a very special case, which leads immediately to a very, very important and very useful and very famous result, which is called ergodic theorem. And it says that if you start a Markov process with a primitive matrix, then you always have a unique eigenvector of the matrix T, which corresponds to eigenvalue 1. You see, the sum of all the columns is 1. So according to the previous corollary, the dominant eigenvalue, which must be real because it's just the maximum of the spectrum, is between 1 and 1, so it is 1, which is not that difficult to see, because if all the sums of the rows are 1, then it means that if you subtract 1 on the diagonal in T and compute your eigenvalues as the roots of the polynomial, you see that the rows are linearly dependent, right, of that matrix, and therefore it must be 0 or must be there. So 1 will be an eigenvalue. Right, and moreover, if you start with any initial condition, any stochastic vector x0, then it will approach very fast in the norm. You know it from the other course what it means. It will very fast approach the vector x infinity, right? So it means that if, for example, coming back to the TV channels, so it's if our matrix T says what is the probability, so the Tij would be the probabilities of jumping from the state I to the state j for each of the couples, then you see that it will stabilize. So this is a very good marketing tool, this kind of Markov chains, and it's also very good tool to provide some estimates, some future estimates of say traffic in networks and things like that, right? So that's extremely important part of applied mathematics, these kind of Markov processes, and the ergodic theorem is an essential tool. And you see now how easily we came to that after going through very few elementary steps in our mathematics, and we are already there, right? So extremely exciting, I guess. So the proof here is very easy. So it's just with this, but essentially there is nothing really complicated there, except of the bit which I left for later, right? The case where the matrix would not be completely decomposable. So where you simply do not have enough eigenvectors. So the geometric multiplicities would be different than the algebraic ones. Right, so there is also the consequence that the matrix itself, so if you take the iterations, so it will converge to the matrix where all the columns will look like the stochastic eigenvector x infinity, which is a nice thing to see. You can easily see that in some examples, and I guess Ioannis will show you, and you will have some tasks towards this direction. Right. The final brief remark handles the more general situation, right? So of course in the real life it's not true that the matrix would be primitive, and then it might be much more complicated, because then you will face the problem that the matrix T can be brought in reasonable basis only into some blockwise diagonal or upper triangular matrix, and so you can just see that if the R would be 0 and the P and Q are themselves primitive, then you can simply do the same thing blockwise. So that's not very interesting. But if R is not 0, then you can use some simple blockwise matrix computation to see how the iterates look, and there are some special cases where you can compute a bit more, right? So this is then a part of what the people call chaos, because the dynamical system which is behind can move really widely, and that's something which is of greatest interest and is too complicated to go for now for us. So thanks for this week in this 101 course. That's all, more than enough, I guess. So have a nice